Question says if 0.42 grams of NH3 reacts with 0.68 grams of oxygen gas, what is my limiting reactant, right? That's the first part of it. I'm starting with 0.420 grams of this and 0.68 grams of O2. Can you guys see that in the back or not quite? The green, is that okay?
The green's
A little hard to see? Okay. Let's try, how about yellow? Is that better? No, yes? I'll write it in a better color for the white part, but okay. All right, we're going to start with 0.42 grams of this. What's it tell you when I get two starting amounts? What does that automatically tell me I'm going to have to do? I'm going to have to do 2 T-charts, right? And I'm going to take them both to the same product. This one says, if the reaction only yielded 78% of water, what was the actual yield? So which product should I take my 2 starting amounts to? I should take them to water or H2O, right? I would be wasting my time to evaluate how much NO I could make because it doesn't ask me about that, right? I could find my limiting reactant by taking them to NO, but I'd still have to do another chart then to go from my limiting reactant to water. So don't waste that time, right? Let's take both of our starting amounts to water. So I'm going to go 0.420 grams of NH3. I think that by this point we should be able to walk through the T-chart okay, so I'm not going to really talk through that as we go. Some of us were still forgetting that in this step of my chart, moles gets the 1. It does not get its coefficient there, it just gets the 1. Because we're telling that 1 mole of this weighs 17 grams. Okay, 17 comes from the molar mass of NH3. And we said we're going to go to moles of water, right? That's the product we want to end up in is water. So these values are going to come from the balanced reaction. Water is going to get a 6, and ammonia is going to get 4. And then last but not least, we're going to get rid of moles of water and go to grams. And we're back to this point now, moles getting a 1. And the molar mass of water is 18. Go ahead and run the math with that. I got about 0.667 grams of water as my possible yield. 0.667 grams. Okay, let's see if that answer seems reasonable. Right? Something I can look at is that my molar masses are extremely similar. And so that means basically I'm going to end up with 6/4 the amount of NH3 that I started with because my molar masses are similar. So I think that answer seems really reasonable. We're going to take our other reactant, 0.68 grams of oxygen gas. Which one is oxygen gas? O2, not just O, it's O2. And some of us, I feel like when we're doing the problems, it would say oxygen gas, and you just try to make up the compound. Or it might say lithium, whatever, and you're going to try to make up the compound. Just look at the reaction and use that reactant, right? I think some of us, when we're doing the problem, it might write out the compound name, and then you're trying to build it. Like, just look at the reaction that's given, okay? So grams of O2 to 1 mole of O2. And so our molar mass here is not 16, it's 32. Moles of O2 to moles of water, or H2O, 6 to 5. And then now we're back to 1 mole of water weighs 18 grams. Okay, multiply across the whole top, divide by the whole bottom.
You get 0.459.
Yeah, good. 0.459 grams of water. And so this answers... So far, this answers one of our questions, right? It tells me which is the limiting reactant. Our limiting reactant comes from the smaller amount of product formed, and so we go back and we say O2 is our limiting reactant, right? I'm not circling water and saying it's the limiting reactant. I'm finding the reactant that caused that halt in production. Okay? So now I need to go answer the percent yield part of it. It says, if the reaction only yielded 78%, what is my actual yield? And so if it says it yielded 78% of water, the equation is actual over theoretical. I'm trying to solve for my actual yield. So what is my theoretical yield? Good. It's 0.459. Would it ever be 0.667? No, we're not going to get to that point of being theoretical. And where does our theoretical yield always come from? The t-chart. It always comes from our t-chart. Okay, and so this is going to go on the bottom, 459. And then there's one other thing that we need to do with that 78%. It's got to be a decimal. Okay, and so before you even plug it in as a percent, I would just go ahead and make it a decimal. 78% equals actual over theoretical. And then to solve for that A, am I going to do 0.78 divided by 459? No, I'm multiplying by 459 on both sides because I want to get A by itself. So times 0.459. Okay, I take that times 0.78 and I get an actual yield of 0.358 grams. Okay, this is where we really need to see, is it reasonable? If you would have got an actual yield of like 10 grams, would that have been reasonable? Is 10 78% of 0.459? No, we need to be able to take a look back and see the big picture here. Does our answer make sense? Because this math is for some reason something people struggle with. Okay, getting that A by itself or getting whatever variable by itself. Okay, questions with that one? 459. I would never, I'm never going to be able to make 0.667 grams of water because I'm going to run out of oxygen first. So once I've determined my limiting reactant, that has to be the only amount of water I could make. Okay, so that's going to be my theoretical yield. Good question. On this problem, I would like for you to do this top question by yourself. Oops. I'm so sorry. I would like for you to do the top question by yourself, and then I'm going to come in and help us with the last part of it here. Do I need to make that a little bit bigger for you guys in the back? Okay, let me do that real quick. But I want you to do this question by yourself, and then I will help with the mass of each product, okay? But I'm going to make this a little bigger for you guys. So this reaction is already balanced. It says if 20 grams of this combusts with 50 grams of this, what's the greatest mass of water that could be formed? Okay, so that means what product are we going to take those two t-charts to? We're going to take it to water. Okay, this part of it, I want you to go ahead and solve on your own. After that, it says if 6.23 grams of water are actually formed, so what's that mean that's going to be? Our actual yield, right? It actually says it, okay? What's the percent yield? So you can do this part, and then I'm going to help us with this second part here. Okay, so I'm going to give you a few minutes to do that. No, okay, unfortunately, no. So the first ones we looked at in class, the smaller one didn't come out to be a limiting reactant. It has to do with not only its molar mass, how much it weighs, but it also has to do with the mole ratio between those two reactants. So it's too hard to predict just based on the starting amounts. You got to actually do the math. In this case, yes, the limiting reactant was the one we started with less of, but that's not always the case, right? Do you guys remember that? We've seen several cases where the one you start with that's bigger ends up being the limiting reactant. So C6H6O3 is the limiting reactant. It didn't ask us for that in this question, so you don't have to necessarily identify that. But what you do have to identify is that once we find out what the limiting reactant is, like this table becomes unimportant, right? We won't get the opportunity to make 14 grams because we're going to run out of C6H6O3 first. And so this becomes my theoretical yield, right? 8.57 grams is my theoretical yield. And so if I go to look at my percent yield of water, I would take 6.23 divided by 8.57, and then there's where we multiply by 100 to get it into a percent. Okay, 6.23, 8.57, 72.7%. Not big concern where you round that percentage. I usually like to have one decimal unless it's really, really close to a whole number. Okay? The last part of this question is really the most complex that they will get. It says, how much of each product could be formed? Does that mean that we need to do 2 more T-charts to go to CO2? No. We just need 1. But what do we start our T-chart with? Exactly. We have to start it with the limiting reactant. There's no use in us doing a T-chart to see how many grams oxygen could produce from carbon dioxide because we know we're going to run out of C6H6O3 before we use up all that oxygen anyway. So I do 1 more chart. I'm going to make myself some room here. I'm going to do 1 more chart and go from my limiting reactant, 20 grams of C6H6O3, and I'm going to go to my second product. So I've already got my molar mass calculated there. 1 mole of it, 1 mole from our balanced reaction. Oops, it's O3. And then CO2 has a 6 there. And then 1 mole of CO2 weighs 44 grams. And so this is the only amount of my other product that I could make, right? I don't need to know the theoretical from the amount of oxygen because I know I'm not going to get to that point. Because it asks for the mass of each product. So I've already solved for the mass of one of my products, H2O, right? I already did that for my previous one. And so now I'm just looking for the mass of my second product, okay, which is CO2. I got 41.9 or no? Yeah. Okay, 41.9 grams of CO2. Okay, and so for questions like that, for questions that ask for the mass of each product, you will need a total of 3 charts. 2 of them tell us the mass of one of our products, because that tells us our limiting reactant. The other one will go from our limiting reactant to our secondary product. Does that kind of make sense? If that's the only thing it asks you, mass of each product, if it doesn't ask you anything about a specific product, it just asks the mass of each product. It doesn't matter which one you pick, to go to twice and then to go to once. It doesn't matter which one you do first. Does that make sense? That's what you're going to see on our homework today is they're going to ask for the mass of each product. So really you're going to have 3 of those charts, 2 which tell us the limiting reactant and then 1 which will get us to our second product. Okay?